Well, thanks very much, Nathan. Thanks for the invitation, and welcome everybody. I can't see everybody, but I gather that you can see me. I'm a retiree now, and so I'm just going to talk about a few bits and pieces that I've been working on over the last few years. And a lot of it's fairly small fry stuff. It's not the big exciting stuff that you Australians deal with. But what I've found is that some of these small things come back and bite you. So I'll just run through a few of these small issues that have come up with mining. And this is research that's still going on. So I'll be talking about southern South Island. A lot of you have been here skiing or whatever. The geology, most of it is the world of the Otago schist, and geologically it's very similar to the Gympie area in that there's hard rock mines, gold mines, and placer gold mines. One of the big things from the point of view of environmental issues is that you can see on the right hand map there, that's the rainfall. We have huge rainfall on the western side, and things are a lot drier on the eastern side. And that rain shadow is has quite a big effect on a lot of the things that we do. I'll talk a little bit about some of the stuff on the western side just briefly at one stage, but mostly I'll be in the rain shadow where it's not too bad. Even Dunedin, where I live now, it's actually quite a nice day. Not a Brisbane sort of temperature, but it's quite a nice day because it's raining. The rain is pouring right down the mountains and has been for the last week. So I'll start off by talking about suspended sediments. And this is something that came up in a seminar somewhat similar to this one right now with industry people about 10 years ago. And we were just talking about what the problems are for the industry from the scientific perspective. And they talked about all sorts of things, you know, acid rock drainage and so forth. But everybody said, oh, of course we have suspended sediment problems, but there's no science involved in it. We just dig a hole and hope. So out of that, fortunately, I had a good and keen student. We thought we'd do some science to try and figure it out, because the suspended sediment issue has been around, especially in Otago here, since the beginning of the placer mining 150 years ago. Back in those days, it was a battle between the miners and the farmers, and there was more miners than farmers, and so the miners could thumb their noses at the farmers, but now you can't do that. Modern mines are larger, there's a lot more farmers, and there's regulations. So the suspended sediment is actually quite a real issue nowadays. So this student did some really interesting work, picked up some different placer gold material, and just tested it for how much suspended sediment it made, what the particle size was, and how long it took to settle. And this is some of the data. The left-hand one, that's a clay-rich one, and so you got lots. The vertical scale gives you an idea of the number of particles, and the horizontal scale gives you an idea of the diameter. So with time, each curve there is a different amount of time for the settling. You can see that over about 2 weeks, you get significant settling, but that's quite a long time when you've got a throughput in a mine. And you compare that with the right-hand one, that was an unweathered conglomerate with, it was fairly solid stuff, and so the particles settled very quickly. So let's look at that from the practical perspective. And this is a large mine in late Pleistocene fluvial gravels. And you can see in the top left, that's the sort of material they're dealing with. There wasn't a lot of clay, and they got rid of the suspended sediments with a number of settling ponds, and you can see on the right hand side there, that was the pathway. The yellow arrow shows the pathway, and just going from pond to pond, it cleared out, and they could discharge straight into the river. That was a very sensitive river. It was a trout fishing river, and so they had to be very careful, and it was actually very successful. And this is because the sediments are fairly well worked fluvially, and this is looking at the sediment in that last settling pond. Most of it is primary silicates. It's like settling ball bearings. So there's very little actually clay minerals in this material, a lot of albite and chlorite. You can see the albite with the sodium map on the right, and the chlorite, the iron on the right at the bottom. So these are primary silicates rather than clay minerals, and they settle quite well. This is another mine where there was a lot more clay. It's also Pleistocene, but it's proximal, so it hasn't been worked so much with the fluvial system when the gold was being concentrated. It's got a whole lot of clay-rich material with it. And most of that was partially weathered phyllosilicates, mainly muscovite actually, lots of muscovite. And when they worked that, there was a fair amount of suspended sediment, as you can see, and they had to settle that, but it did settle through a few ponds, but they had to put a flocculent in to make it settle, and that has a cost. And then they got rid of the water at the end. It wasn't going into a river because this is the dry part of the province. And so they got rid of the water by groundwater soaking into the gravels. And again, if you're adding flocculants, the people downstream get upset when they're saying, oh, you're putting chemicals in our water and so forth. So there is an issue there, but this one, fortunately, the population was fairly low and there was no big issue. So then we come to a somewhat more difficult problem. This is a Cretaceous lithic conglomerate. We did some work on that to look at the settling, and this is an area that was mined quite extensively historically. It's actually where the gold rush started in 1861. It's because it's Cretaceous, it's fairly well lithified, and in fact, this is the stuff that we looked at on the right hand there, the unweathered conglomerate there. There was the Cretaceous lithic conglomerate, and the experiments we did were very successful for getting the settling very effectively. What we didn't realise is that I'll just go back a slide. This is the outcrops that we got the material from, and it had been sluiced and it was all fresh. So the problem was a miner came in just a few years ago and wanted to tackle some of this stuff, and he was getting into the weathered stuff. And with the weathering and oxidation, what used to be fairly solid conglomerate turns into a horrible mush of clay, which you can see going from left to right. The stuff on the left is fresh, and the stuff on the right has got a very high clay content. And that was something that we didn't factor into our original work. So even though we were expecting this material to be pretty benign as far as the suspended sediment, it wasn't. It was dreadful. There was extreme amounts of suspended sediment coming from this, and when you look trying to get the settling ponds to take the clays out, they just totally filled up. They had to be filled out, cleaned out almost every day with this material. And you can see in top right there, the ponds actually overflowed, the clay overflowed, and that's a picture of one of my PhD students. And instead of helping her out, I was wetting myself laughing, trying to take a picture, because she was sinking into this slurry. It was dreadful stuff. And going further than that, because of all that clay, the clay was coating the gold, and that made it much harder to save the gold. And you can see at the bottom left, there's actually interaction, groundwater interaction between the gold and the silicates. So the gold was cementing as well as clay cement. There was a gold cement. It was all holding it together. So that made the clay make a very strong effect on the saving of the gold, and the proportion of gold that was saved was down quite a lot. The gold was very fine grained, and trying to get the gold out was extremely difficult with all of that clay. They were using mercury to try and save the gold from their concentrate, and even the mercury got covered in clay. So we had this combination of clay-coated gold that the mercury couldn't get to, and then the mercury itself got coated in clay and other silicates. And you can see the bottom right there, there's a blob of mercury that is swimming in a whole lot of very fine-grained material. This is a sample that the miner gave me. He said, look, I can't get gold out of it. There's gold in there. I know there's gold in there, but I can't get it out. And this is the reason. The droplet of mercury there was very close to a piece of gold, and we should have amalgamated with it, but it didn't. So this is just an example of a situation where we were surprised, he was surprised, and the end result was that the mine had to be abandoned. He had to give up. So this was a situation where the amount of clay was overwhelming. And that's too bad, because that's the largest resource of alluvial gold in Otago now. There's no overburden. It's just sitting there, but we don't have the technology to get it out. Someone needs to do some more science on the clays. So let's go a little bit beyond that now. We've finished mining a placer mine. We've got a whole lot of gravel. And on the bottom right, this is a modern mine site that's been rehabilitated, and this is the modern process. You go in there and you spread topsoil over it and you plant grass or something like that, and basically you've got a monoculture. And one of the things that I and others have been working on here is the idea, well, can we enhance the biodiversity by taking advantage of differences in the underlying geology, rather than coating absolutely everything with a uniform layer of soil and a uniform layer of vegetation on top? Can we look at something that is a bit more diverse? And on the top left there, you can see there's some historic mine tailings that were just abandoned with no rehabilitation. And these are actually now have a very interesting and new and specific ecological set of niches. So in the top right there and the bottom left, these are things that are not found anywhere else. And on the top left, this is a Google Earth view of those tailings. They've actually been made into a reserve because of their unique heritage. They're dry, they're porous, you can't get much to grow on it, and as a result of that, you get a set of unique ecosystems. Nearby to that, there's another reserve that's been made in a historic placer mine. It was abandoned, and because this is right in the rain shadow, we get evaporative salts sitting on impermeable clay substrate, and that's been colonised by salt-tolerant plants. These are, you have some similar ones in Australia, but these are endemic, and some of them are very rare and actually endangered because there's nowhere else that they can grow with development of agriculture and irrigation and so forth. The environment in which these will grow is shrinking all the time. So as a result of that, this particular site and a couple of others have been made into scientific reserves to preserve these. So these are old gold mines that have unique ecosystems developing on them. And we should try to encourage that sort of thing to enhance the biodiversity. So this is a project that one of my co-workers has started on now near to the sites that I've just been describing, where we've just taken a shovel to an area. This is on a bit of private land. The chap who owns the private land is very keen to have some biodiversity there, so we shoveled off some of the soil to make a place for the salt plants to develop. And this was only last month, so we don't know what's going to happen. But what we're trying to do is just enlarge these unusual niches. So that's the placer world. I'll talk a bit about orogenic gold, because that's where I've spent most of my time, and just over the hill from where I'm sitting now is the Macraes gold mine. It's quite a large one from a New Zealand perspective, 10 million ounce resource. It's orogenic, and it's very low grade, around about 1 gram per tonne. So with the figures I've got on the screen there, there's for every tonne there's 999 grams of tailings, and that's got 1,000 grams of arsenic in it. So arsenic is the main product of the mine, and that of course goes out to tailings. The ore in the mine is very refractory, and so they have to roast it with an autoclave to oxidize the sulfides, and of course the arsenic gets roasted as well, and the minerals in the bottom right there, oxidation in the autoclave. We start with arsenopyrite, you get a bit of arsenolite in the autoclave roasting system, and ultimately it forms ferric arsenate and jarosite and ferrihydrite as well. So these are the things that they're making, and they get the gold out with cyanidation, and the arsenic products in the bottom right there, they go out to tailings. So we've got a lot of arsenic, and one of the things that's been sort of noticeable and interesting, and it's sort of a success story, is in understanding with arsenic. There's been so much work done around the world on arsenic that this is something that we actually know about. And the Macraes mine shows this very well with the autoclave up on the top right of that graph. We've got huge amounts of arsenic in solution, 10,000 ppm or more. And by the time the water comes out of the bottom, the discharge waters from the mine, there's almost no arsenic left. So the processes going through that 6 orders of magnitude dropping of arsenic out of the system is quite spectacular. So what we wanted to know is what are those processes? And the first one is, there we go, precipitation of ferric arsenate. And this is some of the precipitate that you get in the autoclave. You can see the crystals there of jarosite. Those crystals are 1 centimetre or thereabouts long. And as far as we can tell, there's no arsenic in that jarosite. The arsenic is all around the jarosite crystals as iron arsenate, and it, very spectacular separation there. We expected originally to find quite a lot of arsenic replacing either iron or sulphur within the jarosite structure, but there isn't any. It's all inside the iron arsenate. So that's the first thing, precipitation of iron arsenate. And then because the oxidation in the autoclave produces a lot of ferrihydrite, the arsenic adsorbs to the outside, the adsorption of arsenic 5 to that. And that's a very effective way of getting rid of the arsenic out of solution. It sticks to the ferrihydrite, and the arsenic goes out of solution progressively. The third process we think we can identify is because the silicates, a lot of the silicates have been through the autoclave as well, they get turned into clays, and or partially turned into clays, and the arsenic sticks to them as well. Adsorption of arsenic to clays is not as effective as it is for ferrihydrite, but there's an awful lot of silicates within the tailings, so we think that quite a lot of the arsenic sticks there. So that's the third process. And then the fourth process, as the water makes its way just through the system, it finds just little bits and pieces of ferrihydrite and clays all the way through the tailings complex. And so, as well as the adsorption that's going on within the tailings themselves, the water pathway outside this, on its way through the site, and some of it is moving actually through the underlying basement. It trickles out at the bottom end there, and there's essentially no arsenic left at all. So that's just a summary. We've got this chemical evolution from industrial scale arsenic to homeopathic arsenic, from pH 1 in the autoclave to pH 8 as it oozes out the bottom. And that's just a summary on the top left there of the processes. We've got the iron arsenate precipitation, we've got adsorption to ferrihydrite and clay. It's very effective. So from that point of view, heading over to the west coast of the South Island, on the wet side of the island, and that's slightly different geologically. It's a piece of your Victoria. We've got a Victorian slate belt orogenic gold there, and there was a mine that's now closed, 2007 to 2015. The mine over there was sending sulphide concentrate over to Macraes, 700 kilometres, because the autoclave was at Macraes. So that was a feed in the autoclave. Here's the mine, and the difference was, but between Macraes and the Globe mine on the west coast, is that the Globe mine had a lot of stibnite, antimony sulphide. And initially, when you talk to people, they say, oh, well, antimony, it's just the same as arsenic. It's a group 5 or group 15 if you want. Element immediately under arsenic in the periodic table. And there are a lot of similarities in the chemical response of antimony as there is to arsenic. So the hope was that the same processes that I've just been describing in the Macraes system would happen within the whole Reefton system. Well, so the first problem, the processing waters there, they made a concentrate, and that concentrate was full of stibnite, and some of that stibnite at room temperature or air temperature dissolves and so you get antimony and arsenic-rich water. And we're talking about 1 to 10 ppm, which is quite high, actually. To get rid of that, they set up a treatment system, throwing in ferric chloride. Ferric chloride, you throw it into the water and it makes ferric hydroxide. So this is the iron oxyhydroxide, and the idea is that the arsenic and antimony should adsorb to that, just like I've been describing at Macraes. Well, the arsenic did, but the antimony didn't. And you can see in this graph here that on the left of the graph, the treated waters, the arsenic is gone, mostly gone, but the antimony hasn't, because there's preferential absorption of arsenic. It just left the antimony in solution. So this is some experiments that we did over the years to try and understand this. This is chemists doing this. The left-hand side of the diagram, at low pH, you can load up onto iron oxyhydroxide. You can load up antimony, no problem at all at low pH. But as soon as you raise the pH, the antimony drops off. And you can see on the right-hand side there, at pH 6.5, antimony has been desorbed, and at pH 10, it's essentially all gone. So that's with antimony by itself. And then the other problem, which is the one they had at Reefton, is that you got competition between arsenic and antimony for adsorption sites on the iron oxyhydroxide that was made from the ferric chloride. So there's some experiments we did to look at that sort of thing. And you can see the top graph there, pH 3, you load up the iron oxyhydroxide, and over time, the antimony drops off. And take it to pH 5, again, you load it up, but then again, the antimony drops off and the arsenic stays there, just over a matter of hours. And you get to pH 7, which is the pH of most of these orogenic systems, there's no antimony adsorption at all. It's only arsenic. So that's the bottom graph there. We've only got arsenic adsorbed onto the iron oxyhydroxide, the antimony is nowhere. So that was a real problem. And this is what the chemists think is the reason, is that arsenic forms a bidentate ligand. And that's the top left there. It's got two prongs sticking onto the iron oxyhydroxide, whereas the antimonate ion only has one prong, unidentate, sticking onto the iron oxyhydroxide, and that's the bottom right there. So as a result of that competition, if you've got a mixture of arsenic and antimony in solution, iron oxyhydroxide just isn't going to do that, isn't going to do the job. And when it came to the globe mine discharge water, that really showed up, and you can see that here in the graph at the top. The red dots are the antimony in the discharge waters, up around 1 milligram per litre, which is, it's actually quite high for something that is reputedly toxic. So that was a problem. Fortunately, it rains over there, and that problem went away by dilution. But if you were in a dry climate, that would be a major issue. And now that the mine is closed, they're looking at a two-step way of trying to treat this. And at the bottom there, there's some work that I was peripherally involved with, making a bioreactor for reduction of the dissolved antimony. And on the very far bottom right, there's some stibnite, secondary stibnite precipitation on the compost within the bioreactor. So it actually works as far as a pilot system is concerned. Whether it will work for the flow rates from the mine waters, that's another matter. But the thing that comes out of all of that is that to get rid of both arsenic and antimony, you need a two-step process in this system. So what happened to the antimony at Macraes mine? That was brought over to be roasted in the autoclave, and then the material went out to tailings. That happened over from 2007 to 2016, almost 10 years. So, unlike globe, the dissolved antimony remained low. And this is the tailings water at Macraes, the blue symbols there, just didn't have the same problem. And that was good news. It was a surprise, but it was good news. You can see the top there, the red dots, that's what was happening over at the globe side because of the processes I've been talking about. Macraes, it didn't happen. And that's because within the autoclave, the mineral tripuite was made. Now, before I got involved in this, I'd never heard of the mineral tripuite, so I thought I'd put it in that formula in there for you, because you might not have heard of it either. Iron antimony oxide, ferric iron. It's sort of similar to iron arsenate, and there's sort of a solid solution, but not completely. The tripuite has a different structure from the iron arsenate. You can get some arsenic within the structure of the tripuite, and you can see in that triangle, the ternary diagram there, that most of the tripuite we're dealing with is almost half arsenic. But it's quite separate from the iron arsenate. You can't get antimony into the structure of the iron arsenate. You can get arsenic into the tripuite, but you can't get antimony into the iron arsenate. Well, the tripuite is very insoluble. It's very hard to dissolve, and it's more insoluble than iron arsenate. So it's a good news story. If you can make tripuite, you can get rid of the antimony very, very effectively. It'll go into the tailings and it'll stay there. So that's a good news story. Right, waste rock. That's one of the main things they produce at the Macraes mine, large volumes of waste rock, and of course that goes into waste rock piles, which is, these are issues all around the world. And what we care about with waste rock, it's one of the things we worry about is acid rock drainage. In orogenic systems, that's not normally a major issue, and here that's true. Well, the first thing you do when you're planning the mine is do some acid-base accounting, and I suppose you get some samples and you send them to Isles Road in Brisbane or some equivalent, and they'll tell you whether it's acid neutralizing or acid generating. Part of the problem is what you send, and in this situation they did a whole lot. I've got some examples there in the bottom left of just some examples that they did, but they did a whole lot, and it was almost all done on core. There was a whole lot of core material, and that would be a normal approach to this system. So you get an idea of acid-base accounting, and in this case there was no surprise. The waste rocks were very strongly acid neutralizing because there's lots and lots of calcite. It's basically a battle between calcite and pyrite. And on the bottom right there you can see that, yeah, the results were exactly as expected. This is the discharge water that's coming out now of waste rock piles after quite a few years, and it's all pH between 8 and 8.5. So that's a good sign. What the system didn't take account of at the time is that when you take a piece of core, you're getting the interior of the rock, and that's probably what you want to get an indication of. This is the typical rock. But in reality, when you blast it, you've got an awful lot of fracture surfaces exposed on big rocks. And in this case, there's pyrite all over the surfaces. And in this slide, you can see the sort of pyrite I'm talking about. I call it groundwater pyrite. It's just a coating, a thin smear. And when I say thin, some of the crystals in the bottom right there, they're millimetre or 2 or 3 millimetres cubes. And these were not seen in the core. They're deposited by groundwater all over the fracture surfaces. They must have been there in the core, the odd bit, but mostly they weren't seen. Now there's not enough there to change the acid-base accounting. There's plenty of calcite, that's not a problem. The place is swimming in calcite. But sulphate became a huge issue, and that's one thing that we're working on right now. This is an indication of what happens over time for the water composition coming out of the waste rock. And this is a log scale, and you can see that the sulphate, it started off real low, but it just accelerated. The green curve there, the bicarbonate, that's from the dissolution of calcite. It goes up and then it levels off because the waters are actually saturated with respect to carbonate. But the sulphate just kept on going up and up and up. And that graph stops about 2018 or thereabouts, but it's still going up. This is what it looks like. There's the water coming out, and it's precipitating calcium carbonate. It's actually aragonite rather than calcite. There's a tiny amount of gypsum comes out, and if you evaporate it, you don't get any more gypsum. What we want to do is get gypsum to take the sulphate out. If you evaporate it enough, you'll get magnesium sulphate, epsomite, but as soon as it rains, that goes back into solution again. So this is the problem at the moment, to try and get the sulphate to precipitate out of these waters. And there's quite a large volume of them, so it's going to be difficult if you run it through an active treatment system. So here's some geochemical modelling. If you try and evaporate, it's a dry climate, you try and evaporate these waters with a pH of 8, that's on the left there, you're going to get calcium carbonate. There's nothing you can do about it. That's what's happening spontaneously now in the environment. You keep on evaporating it. You have to evaporate almost half of it before the gypsum will start to come out. And even then, it's pretty sporadic. And you've got to evaporate it almost to dryness to get that epsomite, which is too soluble. But on the right-hand side there, this is just modelling. You take the same solution and make it slightly more acid, take it to a pH of 6, then the first mineral to come out with evaporation will be gypsum. The calcium carbonate gets suppressed. So that's the aim. With evaporation and slight acidification, you could get gypsum to precipitate, and the end result of that would be lowering of sulphate. So that's the target. Well, how do you do that? This is experimental work by just throwing the water onto some soil. The soils are slightly acid. You pour the water onto the soil, and lo and behold, in a dry setting, this is done in the lab, but in a dry setting, you get the gypsum precipitating around the roots. So in a lab experiment, it works. This is a direct spin-off of an attempt to figure out, can we irrigate typical soil and get rid of the sulphate? And this was last summer. It works, at least in a pilot study. So in the top left, there's a graph of the sulphate composition of the creek downstream from where this study was done. And you can see that the sulphate got up to about 1,000 ppm, 1,000 milligrams per litre in the previous summer. We started the irrigation trial last spring, and you can see that the amount of sulphate going down the stream was taken right down to below half of what it used to be. And this was just a pilot study on irrigation. And in the bottom right, you can see the effects of that. It's fairly dry in the summer up there, and the irrigated areas are green. Well, the farmer is absolutely delighted with this concept, because not only is he getting green grass at a time when everything else is brown, but he's getting nutrients. He actually has to pay money to put sulphur on his land, and the mine is now putting the sulphur on for him. So this is a good news story too. Whether we can scale that up and get rid of all the sulphate, well, that's another matter, but that's for the coming summer. So I'm getting to the end. These are just some conclusions. Suspended solids, they seem like a trivial issue, but they can be a real problem. The niche geological substrates for enhancing biodiversity, that's just a hobby of mine, but it's sort of fun, and I think it's good. And it's certainly good as far as the communication with the public is concerned. The public can relate to that very strongly. Precipitation of ferric arsenate and adsorption of oxidized arsenic it's very effective. So you can get arsenic out of the water, but getting antimony out of water is very difficult unless you can make that tripurite, and that requires high temperature treatment. At low temperature, at room temperatures, it's going to be tricky to get that antimony out, which is why the bioreactors and reduction is probably what's going to have to happen. And then irrigation with sulphate-rich water, it's a fun project to see if that actually works, because that's a win-win situation. And certainly as far as the local community around the mine is concerned, if they have a water shortage, and if we can make that work, that would be great. So the take-home message is that geological prediction of environmental issues, it's potentially useful, but we've got a lot more to learn from real examples to fine-tune the science. We've got to understand the whole rock mass, and these little things that come back to bite you, they're the scary ones. All right, so that's the end of that.
Thanks very much, Dave. That was a really fascinating talk. It really does show the breadth of the work that you've conducted over the years. I think I just had a quick look. It's probably not something that you throw around, Dave, but I think I noted that you have over 12,700 citations for all of your published work, which probably doesn't capture the whole of what you've done. So thank you for your contribution. It's been really fascinating. We certainly have got some questions coming in online, and for anybody else online at the moment, if you do have any questions, please put them in the Q&A box for Dave below. Dave, I'll point you towards the box as well. If you just click on the Q&A box, you can see some of the questions that are there, but I'm quite happy to direct those to you. The first question that came in was from Bob Cuttress, and I suppose he's alluding to the origin of the mercury that in the placer deposits you were talking about, Bob. So I'm wondering if that mercury is introduced to help recover the mercury, perhaps you might be able to kind of elucidate on the origin of that mercury in the place of sediments.
Yeah, I'm just reading the question there. The mercury still used in placer mining. Yeah, it's used all around the world in placer mining still, in anything that's small. In New Zealand, it's very restricted about what you can use and how you use it. The mercury is recovered with a retort. So yeah, it's still used. The main problem with mercury in the other parts of the world, especially the third world, is that it's not controlled at all, and it has horrific environmental issues downstream.
How much of that mercury in New Zealand is coming from the hypogene mineralization in the Southern Alps?
Oh, none, I think. No. I don't know where mercury comes from nowadays. If you want to buy a bucket of mercury, do you get it from California or Spain? Or, I really don't know.
I've never tried to buy it.
That's what I was going to say. Almaden.
Yeah.
I don't know if it's operating.
Are they still mining there?
I don't know. No, I'd have to check.
So the next question, Dave, from an anonymous attendee, just on the question of rehab of sites. You talked about the biodiversity on the tallings example, but the question is that biodiversity necessarily a good thing? Is there not something to say for restoring the biodiversity and ecosystems back to what was in place before mining?
Yeah, I think that's a really good question. It's a philosophical one, isn't it? The situation we have in most places around Otago now is that it's agricultural. And certainly at the Macraes mine, when they do their rehab, they turn it back into pasture for grazing. And that's a monoculture, really. So from a philosophical point of view, what I'm trying to get across is that for small areas anyway, it would be quite nice to have something that's just a little bit different. And the example I used with the salt-tolerant plants in central Otago, the community and the conservation people agree with that. What they're trying to do is preserve that by making it into a scientific reserve. And there's actually 2 scientific reserves there now. So it's a trade-off. I'm sympathetic with your suggestion there. One of the arguments that people have here is, yes, it'd be good to restore something that was in place before mining, but what was that? Because New Zealand, and I'm sure Australia too, has been modified a great deal by humans over the last 1,000 years. In Australia, probably the last 40,000 years. So we don't actually know what the original biodiversity was in many cases. But yeah, I think it's something that we should all be talking about.
Okay, thank you for that. So the next question is from Anita Babaka-Fox. She kind of has quite a broad question for you, but I think one that you'd be able to comment on quite well is, you touched on the waste rock case study and the sampling regime used to select the materials for ABA accounting. You highlighted that often from drill core, that's not necessarily the most accurate or the most representative approach. Based on your experiences, does the industry need to improve its approach towards ABA sampling? And if yes, what types of technologies or approaches should be adopted?
Yeah, fair comment, Anita. I think looking at the rocks, that's what it boils down to in the end, isn't it? Because when we start off, we're dealing mainly with core. And that's what we have to deal with, because we can't see what the rocks are down there until the blasting is done. So we have to start with that, and then we have to keep on refining it. I think that's the only thing that we can do. As you go down, you see more and more things that are exposed. So the short answer to your question is yes and no, but we need to look at the rocks in the core to start off with. We need to make some predictions, and then we need to refine that. And we need to refine it and refine it all the time. The problem with that is that the first waste rock stack has already been made on the basis of the core, but we can make the other waste rock stacks a lot better by refining things. Is that reasonable?
I think that's a good start. I think it's a big question. It's going to take some while to solve. But thank you for contributing to that. So next question we have, how much is coming? The one thing I was going to ask Dave just very quickly, one of the photos you showed was one of your students sinking in the mud. I don't know if that's the correct occupation health and safety response nowadays, is to take a photograph instead of perhaps trying to salvage them. But in that clay that you had there, is there any possible reuse of that? Is it anything that could be done with that clay? Do they use it as a capping material at any of the other mines that they're closing, or is it something there that's just going to be a problem? Because you mentioned that there was a technological issue with recovering the gold from that clay, but is there anything else that they could use that clay for?
It's not pure enough for, say, ceramics or anything like that. It's got a whole lot of stuff through it. It's got a lot of fine grained quartz and stuff as well. So I can't think of any likely use for it. It was just a nuisance. It really was just a nuisance. And until, I suppose, we have a two-pronged approach in the future for that sort of deposit. One is to follow up on what you just said. Let's find a use for that clay because we know that it's going to be there. And the second one is how do we improve the recovery of the gold? I suspect that cyanidation would struggle because of all that clay too.
Do you know of any work that's going on to actively study that clay material?
No one is. But there are exploration licenses out on that land, so who knows? That's the thing about the gold price now is it's driving all sorts of exploration, and of course any research of that on that sort of subject is going to take years, and of course the gold price will be down again by then. We have to do it in advance.
Yeah.
And of course, no one's prepared to pay when the gold price is low.
So the final question that we have here online is from Tonio Ray Neto, and just asking about your experience with high mercury gold mineral treatment in New Zealand. And they quote example grades of 8 grams per tonne of mercury in ore. If that was the case, what types of technological treatment are used in the metallurgical process to mitigate against environmental and personal contamination? Yeah,
I suspect I haven't got long enough to talk about that one. This is a serious issue. It's a really good question. And I can't give numbers on, what is it, 8 grams per tonne of mercury. The Macraes stuff has got 4% mercury in the gold itself, and so that's probably more than you're talking about. And some of the placer gold has even more mercury in it than that. It's within the gold itself. And the main problem comes when the product is melted. And there's been a number of situations here where I think something that is behind this question, the gold room, they heat the gold product and the mercury goes into the vapor. And 2 places I've seen in New Zealand where this situation's they've had the silver metal coming down the chimney before they realised that there was mercury in the system. and some of the gold workers have had very high mercury contents, and so they've had to be treated. They have this chelation treatment to get the mercury out of people. Once you recognise it, you have proper environmental procedures. You clean the air and ventilate and so forth. But if you don't recognise that, then you have serious problems. And as I say, there's two situations that I've seen here where people didn't know that there was mercury in the gold, and they regretted that.
Okay. Thank you. Thank you again, Dave. That's a great answer to the obviously quite a difficult topic, I suppose, with these high mercury ores. So thanks for that. I think we're now coming to a close. So I'd just like to thank you one more time, Dave. It was again a really fascinating presentation. We have had some requests online for copies of your presentation. I'll talk to you about that later on if you're allowed to distribute that. But certainly, it's been a very well attended presentation. So thank you. The only thing I'd like to do now is just to announce for next week, our speaker is going to be Renji Zhu from the School of Earth and Environmental Sciences at UQ, and he'll be talking about the rise of the Northwest Himalaya, so something very geologically related there. So we look forward to you joining us then. But for now, again, thank you everyone for joining us online, and we hope to see you next week. And thanks again, Dave.
See you later.
Thank you.
Yeah.
Later.